Alright, let's go ahead and do that previous example, but now I'm going to do it using a website here called Thermofluids.net. And if you go ahead and create an account with them and log in, this is what the title screen looks like. And what we'll do is we're going to do what they call test calcs. And this is a flow chart for all the various types of thermodynamic systems that you can solve for. And if we kind of follow this flow chart, we're going to do a system analysis. It's an open system, and if we kind of follow this line that says specific, we come down, we're actually doing a vapor or gas power cycle. So we'll go ahead and select that. Now we get another screen to choose what our material is, and PC is phase change and IG is ideal gas. So we're going to do a gas power cycle. So we'll move down here, and we're not doing a mixture of gases, just a pure gas. And so what we're going to be doing is what's called a perfect gas, which means that we have constant heat capacities. An ideal gas follows the ideal gas law but has variable heat capacity. So we'll select the perfect gas there. And now it brings us to a screen where we enter all the states. And so for example, state 1 is point 1. And here are all my various variables and states that I can add, or properties: pressure, temperature, volume, etc. So what we're going to do is enter what we know. And so what we do is we click the box first. First we got to select our gas. So I'm going to select air. It gave me a little message down here. It says that I need to go ahead and select a working fluid. So now I'm going to click that box for pressure. And the inlet is 100 kilopascals and the temperature is 298 Kelvin. Now those are two intensive variables. So at that point I can just calculate, and kind of like EES, it's going to fill in all the values. So here's my specific volume, internal energy, enthalpy, entropy. It's really kind of nice. It's looking up all the values that you need. So now we'll go ahead and go to point 2. So under state 1, I'm going to move over to state 2. So that's going to be my second state, where we've now done our isentropic compression. And so I need to enter two intensive variables. And what I know is that, well, V2 is equal to V1 over 9. So I'm going to put equals V1 over 9. And I know that my entropy, it's isentropic, is equal to S1. So, and now I've specified those two. I just simply click calculate. And now it gives me my temperature, 718, and goes up to a pressure of 2170 kilopascals. So we can keep moving through the cycle. Let's go to point 3. And point 3, we knew the temperature was equal to 900, and we knew that the volume was equal to the same as it was at V2. So I have to equal V2, click calculate, and it does everything for me. So this is fairly quick. We'll go ahead and move through state 4. State 4 is isentropic expansion. V4 is going to be equal to V1, and it's isentropic, so that S4 is equal to S3. And go ahead and calculate. So there's my four states that I've went ahead and done. So at each point I can kind of click back and through and see what my pressures and what my temperatures are. What I can do now, if I click on this device panel, is each one of those steps would be a particular device. So I've got an inlet state and an outlet state, and this picture shows two actual inlets. We only have one, so all we'll do is we'll leave I2 to null and E2, which is the exit, to null, and we'll say, well, the inlet is state 1 and the outlet is equal to state 2. And it's going to go ahead and solve what Q and W is for me. But first I need to go ahead and give the mass flow rate. So I'm going to come back to the state panel. I'm going to go back to state 1, and I have my mass flow rate. So let's just go ahead and set that equal to 1 kilogram per second. So that it's going to be, all these values will be per kilogram. And I specified m.1, and so let's just go ahead and do that for each one of these states. So this is equal to m.1. Do that at state 3, equal to m.1, and state 4 equal to m.1. Like I should have clicked calculate on all of those. I could also click the super calculate button. It would have done. So now I'll go back to my device panel, and inlet is state 1, outlet is state 2, and state 1 was this was an isentropic compression, which means that Q dot was 0. So if I click 0 for the amount of heat transfer and calculate, it tells me the amount of work that went out, and actually it put in 421 kilowatts, or 421 kilojoules per kilogram, since I specified this on a 1 kilogram basis. And now we'll just go through to our next device. Device B is going to go from 2 to 3, 2 to 3, and what we know there is it was constant volume, so we know there was no work, so that's equal to 0. I can calculate that, and there's the amount of heat that was input, 182 kilojoules per kilogram. And we'll go to device C is going to go from 3 to 4. And 3 to 4 was, there was no heat. And so this is how much work is being produced. 528 in the power stroke. And now let's just go ahead and do our fourth device, which is device D. And that's going to come in at state 4, and it's going to leave at state 1. And there was no work being done there. So I can go ahead and calculate. And there's the amount of heat. And it's minus because it's actually heat is leaving. So 75.5 kilojoules per kilogram. So I can now go back to the cycle panel here and calculate it. And it's going to give me all sorts of stuff. And in particular, here's my thermal efficiency at 58.52, which is the same thing we got using EES.